I'm going to tell you a bit about what are the latest features in LTTng and the work we've done at the analysis level in the past year. So my name is Mathieu Desnoyers. I'm basically CEO of EfficiOS, main author and maintainer of LTTng, Linux kernel and user space tracer. And we have various projects that we are working on. So this is the nice side of having an entire team working on the various projects. We can progress much more quickly. So today I'm going to tell you about LTTng, BabbleTrace, common trace format, LTTng analyses, the latency tracker module, the histogram generator, as well as trace compass. So this is really a focus more on the analysis side, as you will see. So a few words about LTTng. So just a quick reminder. So it performs user space and kernel tracing. So we have LTTng UST for user space tracing and LTTng modules for kernel tracing. So one thing that I need to remind everyone, I mean, I still get this question again and again. So do I need to patch my kernel to use it and things like that? No, not at all. It's an out-of-tree module that can build against Linux starting from 2.6.38 up to now. So we support all those kernel versions, all the stable versions, and no patching is required whatsoever. So you just basically build those modules, load them, and you can use a tracer. You don't have to reboot your system. You don't have to do anything. So, one of the strengths of LTTng is since we are tracing user space and kernel using the same time sources, that enables a seamless analysis of correlated kernel user space data. So the tracer has been created to be very flexible, various use cases, multi-user, going to the network, doing snapshots, light recorder tracing and all. And it's really fast. So the user space tracing, if your architecture allows it, with clock get time VDSO and sched get CPU VDSO, we can actually do the entire tracing of an event while staying in user space. So we don't have to cross the user space kernel boundary while tracing user space. So this is really fast. So what's new? I mean, that's things that we've known for a while previously, but there. So the LTTng 2.6 that we released in January 2015. So we added Java log4j support. So we already had Java JUL support. So we are integrating with the various languages through the loggers facilities that are already there. We added a kernel tracer for syscall tracing. So previously we had system call tracing available, but we could only, it was an all or nothing thing. So we could trace all syscalls or none. So now you can select which of the syscalls you're interested into. We also added, and this is actually something that LTTng does that neither ftrace nor perf have. So we can fetch most of the system call content as long as it's not a complex structure. So we can fetch, for instance, the file name of the open syscall. So it's kind of more useful than having a raw pointer that does not tell you much about the semantic of the information. And we have that. So pretty much everything that's a string, we fetch it. We fetch. Yeah, I mean the string is actually the most useful one at this point. So since Linux 3.17, we took advantage of we started using the work that Thomas Leixner did to allow reading the clock from NMI handlers. So LTTng uses it starting from 3.17. And we added the machine interface also. So LTTng 2.7 now, because I mean January, that's old stuff already. So we are currently in the release candidate phase. So the APIs are stable and we don't add any features. We are only testing and bug fixing at this point. So for LTTng 2.7, so that means that we should have 2.7 final released fairly soon. So it adds support for persistent memory support for the user space tracer ring buffers. What that means is it can be used with either PRAMFS, which is an out-of-tree patch, or with DAX and PMEM, that DAX is in Linux 4.0 and PMEM is in Linux 4.1. So what you can do with it is basically to tell LTTng to use this file system to map the ring buffers of LTTng UST. DAX allows to bypass the page cache, so you're basically backtracking a bit. PMEM allows you to reserve an area of your volatile memory at boot. So what you can do then is to put a file system into this, and PMEM actually exports this memory area as a block device. Then if you use, I think so far there's ext2, ext4, and perhaps XFS, but I'm not sure, that have DAX support. So when you mount with the DAX option, it tells the file system to bypass the page cache. So there you can mmap a file, and directly when you write to those memory addresses, you're actually directly writing into the file, into that in-memory file system, directly to memory. So the nice thing about it is if you have a soft crash, kernel crash, or things like that, you can do either a soft reboot if you have a BIOS that do not reset memory on reboot, or you can use kexec to chain load into another OS. So you can kind of prepare the new OS in advance, and then kexec just to bootstrap the new one. And then you can remap into that same memory area and get that same file system. And I created the LTTng crash tool that actually takes those in-memory buffers in whichever state they were and regenerates a CTF trace out of that. So you can actually get the trace that was just before your crash. So it's currently done for UST. I did not have time yet to do it for LTTng modules, but that should be coming fairly soon also. Yes, can you pass the microphone,
please? Just wanted to ask, a DAX memory or PMEM memory can be order of magnitude slower than standard RAM device. So
no. There you are. They're actually, I mean, that's the fastest device you could get. You're directly using memory.
It's fastest as a storage. It's not as fast as a RAM device. I mean, because of the bus, it uses PCIe bus.
No. You can use DAX on non-volatile memory. That's specific hardware from Intel and everything that's coming and everything. But you can also use that with volatile memory, your standard RAM, with PMEM and DAX mapped into standard RAM, and this is as fast as RAM.
Okay, I see. And I have a question. Assuming you would use DAX on a NVD or other fancy non-RAM device, would that is LTTng tracing facility synchronous? So would it be affected by the lower speed of the underlying device?
So you should talk about that to Mathieu Wilcox. He could answer your question.
Yes.
I mean, if the CPU kind of needs specific instructions to be executed to ensure that the data has been committed to those devices, LTTng do not issue them. So if you depend on that, I mean, there might be some tweaks to do to LTTng to support that. But I mean, if it's just that we write to the memory mapping and we go as fast as we can, and the CPU is actually kind of taking care of pacing us down if the bandwidth is throttled, I mean, yes, this is going to slow down your tracing a little bit, and that's it. But you should be able to use it.
Will this affect also the standard workflow? I mean, on the function you're tracing?
Yes,
okay.
Because you are directly tracing into those buffers from your actual code. Yeah.
Thank you.
Yeah, you're welcome. So you can try it today. I mean, it's currently it's in the stable-27 branch of LTTng UST and LTTng module. So other features coming in 2.7, LTTng filtering for kernel domain. So we ported the filtering that we have for user space tracing. We ported that to the kernel. So it's a tiny bytecode interpreter that has. So when it receives the bytecode, we validate that there's no out of bound. I mean that the bytecode is actually valid. It's not going to generate anything bad on the system. And then we can do the bytecode execution quite quickly. So it's really just for filtering. So we added per process user space and kernel tracing, so we can select a list of process IDs that we're adding and removing from that tracker. So within a session, you can actually add and remove PIDs. So rather than tracing everything on the system, you're only tracing a subset of processes. So we're adding also wildcards for kernel trace point. So you can do enable event sched star with a wildcard, and it's going to enable all the scheduler trace points, for instance. Don't forget the single quotes. It's important. LTTng modules, clock plugin support, and UST clock and get CPU plugin support. So this has been requested to us by customers who are using LTTng on ARM systems, and ARM do not implement VDSO for reading time and getting the current CPU number. So they're kind of bypassing that by doing their own implementation. So we are also adding Python logger integration within LTTng UST. So you can now trace from Python. So whatever Python program that already outputs its log through the Python logger, you can connect LTTng UST and gather those information through the same buffers that you will with all the same facilities that you can use streaming to the network, snapshotting mode when there's an issue that occurs. So you get all the features, and you get correlated information between what's being saved through those loggers and what's happening at the native code level, what's happening at the kernel level. So an update on what's happening on the BabbleTrace front. So the current stable BabbleTrace is BabbleTrace 1.3. It consists of really a CTF, a common trace format reader. It allows merging CTF traces by timestamp. So it's actually marshalling all the files and giving. Actually, it's a kind of we just traverse all the events in ordered fashion and call a callback. It supports live LTTng tracing, so we can consume live traces, and it provides C, C++, and Python APIs. So what's coming? We've been hard at work on BabbleTrace 2.0. So our current approximate release date is probably going to be October 2015, but it's a big undertaking. So we're doing a plugin system overall so that external plugins can be used with BabbleTrace. Because currently, I mean, if you want to create a quote-unquote plugin, you actually need to put it into the BabbleTrace tree and be aware of all the plugins that are there and everything. So now we're doing really a proper plugin support based on DLOpen, so that external trees can implement their own plugin, and BabbleTrace could be told about where to look for the plugin list on the plugins that are available on the system, and it's going to consider them. We are also doing a trace intermediate representation. If you look at the common trace format, a big part of it, I mean, so just a small recap of CTF. So we have a model and a description of the trace layout, and we have binary streams. So you can get the very small traces with this. So one thing we notice is that this object model that we're using to represent the layout of a trace, we can actually reuse it as an intermediate representation of a trace. So whatever is being fed by an input plugin can be put in this model, and we update the model as we traverse the trace of the each streams have their events, and so we have the current state. And then this model is being used as an interface between an input plugin and an output plugin. So I mean, it's a huge cleanup that we're doing. So that should be a really rock-solid basis to continue further on. And we're planning to add event filtering also on top of that. So work ongoing on the common trace format. So we are currently designing a few changes for CTF 2.0, and the main thing that we're doing there is transitioning our metadata, so the trace description grammar that is currently a custom grammar called TSDL, Trace Stream Description Language. We're planning to move to JSON. And the main reason for that is that some people expressed interest to do their own CTF reader implementations in various languages. This is the main reason. I mean, we're providing BabbleTrace with bindings and everything, but some want really native implementation of their parsers. And having to implement a parser for TSDL seems to be I mean, to represent an effort larger than most people are willing to do. So the specification of CTF 1.8 is available on the Daemon website. I can actually show you. So it's a web. So it's being put in a web interface, and we've actually added nice diagrams as well as pretty cool examples of. Let's say that you take. Yeah, the screen is a bit small, but there you can. Let's take a more interesting example. So if you take a structure, so this is really the link between what's at the TSDL level. Perhaps, yeah, I can make it larger. So you have a structure with a few fields, and then we have highlighting. So if I highlight this, so this is really just to show people a little bit what's happening there. So you have the description that describes this field. We're hovering over the actual hex representation in the stream, in the binary stream, and this is associated with a specific field value that is going to be shown in the trace output. I mean, that's just those are just some kind of a very specific example of the various cases, but it's useful if you want to get a better understanding of what's happening in the common trace format. So LTTng analyses. So it's a new project we started in the past year. It's a set of Python scripts that provide summarized trace information. So we tried to look at things more from the end user's perspective, and I should say that Brendan Gregg has been a great inspiration to us. With the various scripts, you can actually tackle various issues. Think about workflows, what you want to investigate, what are the type of problems a user is facing. And to be frank, providing gigabytes and gigabytes worth of trace data to a user that's facing a problem, if the user is not a huge expert in operating systems, that's pretty much worthless. So we have been hard at work on analysis, and we figured out from looking at various scripts, including Brendan's scripts, that we could classify most of those analyses in three categories. So a top analysis, providing top N. Let's talk about latency for now, because this is what tracing is very, very good at. So top N longest latencies found. Statistics table, so average, standard deviation, minimum, maximum, and frequency histogram. So what's the distribution of the frequency? So the available analysis that we currently have. So we have many. So we have CPU usage, migration count, memory usage, I/O usage, I/O latency, operation log, interrupt handler duration, top log statistics, frequency trail. We have soft IRQ handler latency statistics and syscall usage statistics. So I mean, you can have a look, and this is a good basis to actually extend and create more analysis. This is really the goal there. So I can actually do a small live demo. So I took a trace. So I have it on my laptop. Is it large enough, or I should increase the screen size? Increase. So zoom in. There we go. So I just took a trace with the, well, let's do it live. LTTng analysis. I just checked out the project. I can do LTTng dash. Oh, let's see if I have a LTTng session daemon. Yes, no. So I'm starting a session daemon. I have LTTng deployed in this laptop. So I start recording what's needed for the analysis. I can do something like run top or something, move it around, and then I stop it, and I can launch my analysis on top of that. So I can do, for instance, let's look at IRQ. Let's do the IRQ frequency, for instance, or stats. Let's do stats. So it's computing. So currently the goal has not been to do fast analysis. I mean, Python is very, very slow. We'll have plenty of room for optimization later, but the goal of doing all these analysis in Python is that it's really, really fast to prototype. So there, we have the table. I'm going to reorganize it a little bit. There we go. That's better. So here we have the each hard IRQ with the device it's actually servicing. We have the count, and we have their duration. So I'm going to show that same thing for the frequency trail, just so you have a sense of what it's doing. And this is a really short trace, so you can see it takes quite some time to compute. I just took it on my laptop. I mean, it was about 10 seconds, not much happening on the system. As soon as you have a loaded system, very heavily loaded and all, it can take a while to compute. But I mean, we have plenty of room for optimizations to do in those scripts. I mean, the first thing we have in mind is actually to implement a filtering bypass directly in C. So for everything that the analysis is not interested in, we don't even send the events to Python. So that would be the first thing to do, which is not done yet. So we can see here by interface, we can see the latency distribution. So you can see the y-axis is actually the buckets of latency, and you can see the diagram shown. So we have it on a per device basis. So this is, for instance, for my network interface. This is in microseconds. So we can see that the top latencies are 9.7 microseconds. And the other one that's actually interesting there, if we just stick to IRQ, because otherwise that would be a bit much. We don't have the top for the IRQ. Well, this one has not been done. But if I had the top one, then I could look at the top duration of the enders and know exactly at which timestamp they were occurring. Actually, I can do the same with the IRQ log. There's an option to actually put a cutoff. So only show the log of IRQ endler that lasted more than that much. And then we could find the timestamp of those IRQ endlers. But I'm not going to go through that because that's going to take a bit too much time for what we have. Yeah, that's it for LTTng analysis. I would say we put our main focus on block device activity. Oh, there's a question at the back, if you can bring the microphone.
Do those analysis tools allow you to filter by core?
I don't remember. Let's have a look. So let's do LTTng RQ quick -- help. Man, let's start IQ. Not currently. One thing you could do, though, as a hack, you could just remove the CTF files for all the cores you don't care about and run the analysis there. Try it out. I'm not sure it's going to work, but you can try it out. Yeah. So, and that's going to be actually much easier to do once we add the filtering capabilities directly in BabbleTrace, because all those analyses are built on top of BabbleTrace. So when we'll have that, we will be able to say to allow the users to perhaps pass their own extra filtering that they want to apply before the analysis is performed. The other thing we want to do with BabbleTrace in the upcoming one is to allow the users to use it really as a, let's say, a trace cut facility with filtering. So you can take a large CTF trace and then say, okay, I just want to cut, I just want this CPU, this process during that time frame, and it's going to generate a CTF trace that is much smaller, that has only the information you're interested in. So this is also coming. So now moving on to the Latency Tracker. So it is a kernel module that's completely separate from the LTTng project. It's self-contained. It can be used to track down latency problems at runtime. So think of it as a very, very, very specialized dtrace. So there's no language. It's not the user who's implementing what they want to do within those when the tracer is called. It's a very dedicated tracer. So it's a simple API that can be called from anywhere in the kernel, any execution context, from kprobes, tracepoint, netfilter, hooks, or hard-coded calls. So, and it keeps track of entry and exit events and calls a callback if the delay that has been specified by the user has been reached, if the threshold has been gone over. So the API is as simple as this. So you create a tracker, you have an event in, event out API, and basically, so you and the key thing there is you provide a key that's used to match the in and out events. Underneath, we're implementing the tracking of those with a hash table. So if the delay is higher for a specific key is higher than the threshold specified, the callback function is called. And we have also a timeout parameter for the cases where, let's say that you have an event in that come in, and for some reason the event out is either never reached, or it takes ages before it is actually reached. So we have a timeout parameter, so we basically can trigger the callback even if the event out has not been encountered once we reach the timeout. So the use cases that have been implemented so far. So we have the latency tracker for the block layer. So it detects a delay between block request issue and complete. Wake up latency, delay between sched wake up and sched switch. Network latency as a prototype, hierarchical and lower latency, as well as system call latency and up CPU latency. But I'm going to, I think we have another presentation on that today, so I won't go into, well, actually we do have many details. So on syscall entry, for instance, so you have the event in, the current PID, event out on syscall exit, the current PID. And then on sched switch, you can actually do a check on the on whatever is being switched. If it goes over a specific threshold, then you can do stack dumping. But again, I'll let François tell more about this later on today. So this is what it's giving is actually system call latency. So basically, you put you can change the threshold dynamically, and then you can get a trace of all the stack dumps that correspond to the long syscall latency. So you can see what was calling this syscall and what state it was. So there's also up CPU profiling. So on sched switch, event in, event out with a callback. On sched wake up, again. So the idea there is you're basically just working on sched switch and sched wake up. Sched wake up is actually going to take a stack dump of the waker process, the process that performs wake on the other process. And if that other process was up CPU for too long, then we're going to take a stack dump of the waker. So it provides this kind of output. So on top of that, still a self-contained module. It's not exporting any trace buffers, nothing. I mean, it's really just doing its computation in the kernel. So we added the support for runtime latency distributions. So this one is pretty cool. So it's now merged into the Latency Tracker tree. So it's going to show a distribution of request latency. So currently we have disk.io latency distribution. I'm going to show a small video demo about it. Okay, so this is showing, let's start it a little bit. So basically you cat a profile that is a block kist tracker here. And what it's showing is so the latency range at the left. And you have then columns about syscall. So this is really, you can see it as a distribution of your latency. So the y-axis is the latency duration, and this is a logarithmic scale dimension. So the other dimension is really slices of read syscall, write syscall, read and write, sync, close, or open and close. So this is really the latency at the syscall level. Then we have the file system layer, we have the I/O scheduler, and the block layer. And then we'll be able to see, as I start the video, the various numbers changing. So we take every second we cap the file, and it's basically updating, sampling the counters during that second, and it's going to be done with some activity. So we're dropping caches, we're doing a DD of 0, and then we can see what's happening. So at the syscall level, file system level, the I/O scheduler, and the block level. You can even have a sense of what's hitting the page cache. and what's hitting the disk, and where are the longer latencies, at which level of the block I/O stack the latency is located. So this can be quite useful. So some of the ideas we have is to eventually, so with the latency tracker, then we could integrate that with LTTng doing flat recorder tracing. So we could basically, so with the latency histograms, we can actually figure out what are the standard deviation, what are the 6-time standard deviation, for instance. So we can have adaptive snapshots that are taken. So when we go have too many latencies that go over a specific threshold, then this might be an interesting spot to look into the system. So we take flat recorder traces all the time, but only snapshots when we find weird things or long latencies happening. Okay. So the overhead, if we compare that, so with the sysbench benchmark, so with the baseline, so LTTng with just tracing scheduler has an overhead of 0.61%. If we trace the syscalls 2.66%, and I have to say that a lot of this overhead is actually due to the Linux kernel entry 64 or 32.s that has non-optimal ways of letting other tools hook into syscall entry and exit, because it saves all the stack for the sake of ptrace. But for tracers like this, we should not need that. I think NP Luminosity is currently working on this to improve it for secure computing and tracing and other things. So a lot of this overhead should go away fairly soon in newer kernels. So the latency tracker here, 3.31%, and we have latency top for 4.7%, and then all the LTTng instrumentation enabled, 11% in this case. So basically what we can see there is that the latency tracker and latency top, the latency tracker here is not much more expensive than doing a specific tracing through ring buffer, so it can really compute on the spot what's happening. So a few words about the TraceCompass project. So we have started being involved more heavily with the TraceCompass developers. We now have at EfficiOS one TraceCompass maintainer within our team. So TraceCompass is now available as a standalone application. It requires only a Java virtual machine to be run, so you don't need the full Eclipse thing. You can just get TraceCompass if you want. It's available in a brand new website, TracingSummit2015.org. So it's really so you get all the basic information about features, the format supported, analysis and view, and how to get it, which is, in my opinion, the most important part. Yeah, you get all the information you need and links to documentation. So we are currently working with the TraceCompass team to facilitate the workflow of back and forth between LTTng analyses and TraceCompass. So the idea there, I mean, the workflow we have in mind is really you kind of have a problem to tackle, you want to investigate an issue, and you don't necessarily want to look at things. I mean, TraceCompass is very good at showing very detailed information about a short time range, but it does not provide necessarily as high-level information as the LTTng analyses are doing. I mean, eventually it can be implemented, but I mean, the batch analysis approach that's quick and easy to do. I mean, it could be custom analysis that people are doing. To me, is always going to be complementary to a full graphical tool. So, so we're trying to make sure that going between you have an analysis, you find a timestamp that's interesting, how you can bring that into the tool and go back and forth between the two is easy to do. And now TraceCompass can read the perf traces that are converted to the common trace format. So perf now has an option to convert to CTF. It's being merged mainline. So this is an example screenshot of TraceCompass with this is a kernel trace being shown in TraceCompass. So that's pretty much what I have. You guys have a question? Yes.
I saw some discussion earlier about integration with BPF. How does that work?
So we are not integrating with the eBPF in the case of LTTng. So I think Suchakra is going to present in a lot of detail later on today about this. But I mean, the equivalent of eBPF that we have in LTTng is the LTTng bytecode interpreter that I created initially for LTTng UST for user space. Then I reused the exact same thing for the kernel tracer. So the main difference between eBPF in that case and the bytecode interpreter of LTTng is that eBPF is really generating machine code. So in that respect, it's faster than the LTTng bytecode interpreter. However, I mean, when I initially did the LTTng bytecode interpreter for user space context, you have to be aware that sometimes it can be trickier to actually play with the executable mappings of user space applications under specific security constraints and things like that. So I wanted something that was only using data. So it's a bytecode interpreter that is code, but it's a shared object that is loaded, and then everything that's passed by the user is actually bytecode that's being played with as data. It's non-executable. It does not need to be in an executable page. So this was really the reason why I did the bytecode interpreter. And in addition to that, I wanted to have this bytecode interpreter because first, it's architecture agnostic. Second, if we want to port to every architecture, it can be first used as a fallback. I mean, it can always be used as a fallback to execute bytecode. We can always eventually implement a JIT, implement a translation from bytecode to native code, but I thought that would be more an optimization and should not be the first and primary implementation. Because, I mean, so even if you're on an architecture where you have this translator to native code, if you execute in a context where the user, for security reasons, do not allow you to populate this executable information, then I mean there's always the fallback of using a bytecode interpreter. So this is why I focused on that part first, and it turned out to be fast enough for my customer needs. So I did not need to go further than that.
Thanks.
You're welcome.
Anyone else? Yeah.
Okay. Well, thank you very much.